see the topic transitivity. Transitivity is basically asking, if two of my friends know each other, how likely is it that I also know them too? In networks, this is measured by counting triangles. So if A is connected to B and B is connected to C, we also check if A is connected to C. A high transitivity value means the network is tightly knit. Think of a college WhatsApp group. If most members are friends with each other, transitivity is high. Another example is in research collaborations. If two researchers often work with a third person, transitivity measures the chance that they will collaborate directly with each other. So if a person A is connected to B and B is in turn connected to some other friend C, are A and C also connected? This is what transitivity is. So its mathematical representation can be seen in this slide. So for a transitive relation R, A capital R B, that is A relates to B and B relates to C, then A relates to C. This is the mathematical representation of transitivity. So you can see in this graph, when V1 is connected to V2, V2 is connected to V3, hence V3 is connected to V1. But is this true always? That is what we are trying to find out. So in a social network, what does transitivity mean? Transitivity is when a friend of my friend is also my friend. So if you have a friend, is the friend is also your friend, is his friend also your friend, then there exists transitivity. So the transitivity in a social network will lead to a more denser graph and eventually a complete graph. So we will find out how complete a graph is by finding out or by measuring transitivity. To find out transitivity, we have to calculate the clustering coefficient. So this clustering coefficient will measure the transitivity in an undirected graph. So there are two types of clustering coefficient. One, global clustering coefficient, and the second one is local clustering coefficient. So let us see what is global clustering coefficient exactly. So what it does, it will find the closed path of length 2 and it will divide by the paths of length 2. Between every node is a triangle. There are two closed paths. So we will find out, we will multiply number of triangles into 6 because there is a transitivity in a triangle, and if there are 3 nodes in the triangle, then the number of edges should be 6. So divided by paths of length 2, this will give us global clustering coefficient. This formula can be rewritten in another way. Number of triangles into 3 divided by number of connected triples of nodes. Okay? So, number of triangles in the graph you can find one by one by just looking into the graph multiplied by 3 and divided by number of connected triples of nodes. Okay, now let's talk about triples. A triple is simply, the word itself says, 3 nodes. If only 2 edges are present, it is an open triple. If all 3 edges are present, it is a closed triple, which forms a triangle. In LinkedIn, imagine if Alice knows Bob and Bob knows Carol, that's an open triple. But if Alice also knows Carol, then it's a closed triple. In school friend groups, If you have two friends who also know each other, that's another closed triple. So clustering coefficient is really about how many of these triples are closed in the network. Now let us understand what is or what does triple mean in a graph. Triple is an ordered set of three nodes. So if there are three nodes and if they are connected by two edges, then this is called an open triple. And if there are three nodes and if there are three connected by three edges, meaning if all the nodes are connected by each other, then it is a triangle or a closed triple. So that is a closed triple. Now let us find out when does triples are known as same triple or different triple. Pay careful attention. Same triple or different triple. So let us understand first the different triple. So when do we call two triples as different triple? The first case is obviously when there are different nodes for both the triples. Obvious. If one triple has edges on nodes V1, V2, V3 and the second triple has the nodes V2, V4, V5, V6, then they are two completely different triples. But the second condition arises when the nodes are same but still they are called as different triples. Understand this. So here we have an example in the box. We have two triples here. They are Vi, Vj, Vk and Vj, Vk, Vi. Here these two triples are said to be different triples but they have same numbers. So let us see why are they called as different triples. If you look at the first triple, Vi, Vj, Vk, these has the edges from Vi to Vj and then Vj to Vk. This is Vi, Vj, Vk has edges from Vi to Vj and Vj to Vk. So what is the missing edge here? The missing edge is between Vk and Vi. There is no edge between Vk and Vi. Let us look at the second triple. We have an edge from Vj to Vk and the second edge is from Vk to Vi. So the edge that is missing here is between Vi and Vj. So here the missing edges are different, right? The first triple has missing edge between Vk and Vi and the second triple has missing edge between Vi and Vj. Clear? Hence, they are called as different triples. If you look at the second box, they have given another triple example. We have two triples here, Vi, Vj, Vk and Vk, Vj, Vi. So there are said to be same triple. Let us see why. Because there exists edge from Vi to Vj and Vj to Vk. Similarly, there is Vk to Vj and Vj to Vi. The edge that is missing here is between Vk and Vi in both the cases. So they are called same triple. So any triangle will have these three triples. A triangle will have three triples and for every triple you can miss any one of the three edges. I hope you are clear. The global clustering coefficient is about the entire network. So we count all possible paths of length 2 and check how many of those paths are closed into triangles. This gives us a sense of overall tightness or community feeling in the network. Take for example the Facebook hobby group. If everyone in the group knows everyone else, the clustering coefficient is very high. In a workplace or email network, a tightly networked team will form many triangles showing high clustering, while a more scattered company might show low clustering. So let us look at an example here to find the global clustering coefficient. We have a graph with four edges, V1, V2, V3, V4. So what does the formula say? C is equal to the number of triangles into 3 divided by number of connected triples of nodes. So number of triangles that you can see here in this graph are two. The first triangle is V1, V2, V3 and the second triangle is V1, V3, V4. So we have two triangles into three. Fair enough. Let us look at the denominator. So since we have two triangles, it means there are six triples, right? Because every triangle will have three triples, so we have again written as 2 into 3 because we have two triangles and every triangle will have three triples plus 2 because there are two extra triples that you can see. One is V2, V1, V4 and the other is V2, V3, V4. These are the two other triples along with the six triples formed by the triangle. This will give us 0.75, meaning 75% of the transitivity exists in this graph. Now let's try to understand local clustering coefficient. So in global clustering coefficient, we saw the transitivity in the whole graph, whereas we will see the transitivity at the node level. I repeat, transitivity at the node level is called local clustering coefficient. Global clustering looks at the whole network, but local clustering zooms into a person, one person specifically. It asks, what percentage of my friends also know each other? For example, a Twitter influencer may have thousands of followers, but most of these followers don't know each other. So their local clustering is low. On the other hand, in a workplace, a project team where everyone knows each other shows a very high local clustering for each member of the project. So this is employed mostly for undirected graphs, as I have already told, and what this local clustering coefficient finds out is, it finds out how strongly the neighbors of node B are themselves connected. Okay? So this local clustering coefficient is given by number of pairs of neighbors of Vi that are connected divided by number of pairs of neighbors of Vi. So for an undirected graph, the denominator can be written as di into di minus 1 divided by 2. So di here means the degree of the ith node. Okay? So let's give a typical scenario which is called structural holes. Let me start with an example. Now, this concept happens when one person connects with two groups that otherwise don't talk to each other or not connected between each other. Such people become bridges and have an advantage because they can share unique information across both different groups. Think of LinkedIn networking. A consultant who connects the healthcare industry with IT companies is filling a structural hole because these two groups normally don't interact each other. Another example is in a university. If a student belongs to both a drama club and a coding club, they act as a bridge between two disconnected communities. So finally, let's look at an example of local clustering. Suppose on Instagram, say 10 people. If 9 of those people also follow each other, your local clustering is very high. In a workplace Slack channel, if everyone in your team communicates with each other, you have a high local clustering coefficient. But if you are a part of a cross-departmental team where members don't know each other, your clustering coefficient will be lower. So this example helps us to understand the difference between dense and sparse friend circles around a person. So let us discuss the example shown on the slide. We have three graphs here and we are trying to find out the local clustering coefficient of V1 in all these three graphs. So C is connected to C of V1 is 1 here in the first graph. Let us find out why. So here V1 is connected to 3 nodes, right? So its denominator will be 3 into 2 divided by 2. This will give us 3, and the numerator, how many nodes is it connected to? 3. So 3 divided by 3 will give us 1. In the second graph, again the node V1 is connected to 3 neighbors. So the denominator will be 3. But the nodes are connected. How many nodes are connected here? How many nodes of V1 are connected here? Only with one edge. It is 1 by 3. In the third case, V1 is connected by 3 nodes, 3 of its neighboring nodes, but none of its neighbors are connected to each other. So it is the local clustering coefficient in this case will be 0. So what do we learn from all these measures? Transitivity, clustering, centrality and structural holes. Well, they are not all just abstract formulas. They are secret detectives of social media data. They tell us whether we live in tight-knit friend circles, act as bridges between groups, or just lurk in open triples, hoping someone will connect with the dots. In short, studying these measures helps us to see patterns that even Facebook or Twitter themselves might not admit to. Like why a college WhatsApp group feels like a family, while your LinkedIn connections feel like some distant cousins who visit or appear only for Diwali greetings. Okay? So, next time you are scrolling through social media, remember, behind every like, follow or DM, there's a triangle, a cluster or a structural hole waiting to be measured. And that's the beauty. Social media isn't chaos. It's mathematics in disguise with a funny profile picture.